Good morning. We are going to start today with a quick little lesson on our number system and how the numbers got developed and how to classify them. I'm sitting on the floor of our classroom because we're going to use these boxes to help kind of demonstrate as we're going through. And I'm going to tell you a story. So I'm going to tell you a story of how humankind developed the number system based on what they needed to do at the time. So we're going to start with our most basic numbers, and that's the natural numbers. This little N with the double strike through, that is the symbol that mathematicians use to say natural numbers, and those are just our counting numbers. So inside our set of natural numbers is just the numbers 1, 2, 3, 4, 5. In the beginning, people needed to be able to count how many cows they had, count how many children they had, count how many steps they were from the water, things like that. So we're literally counting things that we can count on our fingers. So our natural numbers are our counting numbers, 1, 2, 3, 4, 5, okay? Now, humankind, as they were developing, started to have a need for zero. They needed to be able to say that they had nothing. So again, over time and in many different parts of the world, kind of at the same time, humankind developed the number zero. And that brought us to our whole numbers. So whole numbers, W with the double strike through, we're gonna write this later, so don't worry too much about it. Our whole numbers are just the natural numbers, 1, 2, 3, 4, 5, and zero. So now our set is 0, 1, 2, 3, 4, 5. Now notice all of our natural numbers, all of our 0, 1, 2, 3, 4 are in this set, plus the set, plus the number 0. So what that means is our natural numbers is a subset of our whole numbers. The natural numbers fits completely inside. So that's a subset. So whole numbers, again, are our counting numbers, our natural numbers, and 0. So 0, 1, 2, 3, 4, 5. Now, for a long time that was enough. But then people needed to subtract and take things away, which was fine if you were doing 10 minus 7. But if you needed to do 7 minus 10, the natural or the whole numbers didn't do it for you, because 7 minus 10, you all know, is negative 3. So that's no longer one of the numbers that they knew, which brought us to integers. Now, don't ask me why. It's a Z with the double strike through. It's some foreign language, I don't know, but that's the symbol we use for integers. And what the integers are, it is, I'm going to read it, a number with no fractional or decimal parts. It's not a terribly mathematical definition, but it gets the point across. What it's going to include is the natural numbers, 0, and the opposites of the natural numbers. So this set is now inside this box. The dot, dot, dot means forever in both directions. Negative 3, negative 2, negative 1, 0, 1, 2, 3. So it doesn't include 0.5. It doesn't include 7 2/3. Doesn't include pi. It includes only the natural numbers with 0 and then the negatives. Now, again, notice all of my whole numbers, 0, 1, 2, 3, 4, dot, dot, dot. All of those are also integers. So that fits inside of this box. Our whole numbers is a subset of our integers. Okay, so again, what we've done is take our whole numbers and added on top of that the negatives. Negative 3, negative 2, negative 1, negative 23, negative 627, all of those numbers, okay? Now, what happened from there is people needed to be able to divide. Again, perfectly fine if you're dividing 10 divided by 2. 10 divided by 2 is fine. 5, that's still an integer. But what if I needed to do 2 divided by 10? Well, you know that's 1/5, not an integer. And that's where rational numbers comes in. Again, don't know why we use a Q. So it's the Q with the double strike through. Now, this one has a kind of a complicated definition. Can be written as a quotient of 2 integers, P over Q, where Q isn't equal to 0. I have to say the Q not equal to 0 because you can't divide by 0, ever, it causes the end of the world as we know it. So basically it means that it's a fraction of integers, okay? So this is going to include Integers, because every integer can be written as that number over 1. So negative 3 over 1, that's a fraction of integer. It includes fractions, it includes mixed numbers, and it includes decimals if they terminate in or repeat, okay? So here's some examples. I can't do it in that set notation because it's infinite, and these are just some of the examples. So some of our examples here, negative 3, again, I can do that, negative 3 over 1, 1/5, already a fraction, 0.232323 ... it's repeating, so it's okay. It's a rational number. 25.67, it's terminating, so it's okay. So that one is a rational number. And then 12 3/4, it's a mixed fraction. I can do that little loop thing and make it to an improper fraction, and it'll be a fraction of 2 integers. So those are just some examples there. Now, once again, notice all of my integers are also rational. So integers is a subset of our rational numbers. It goes all the way in there. So if something is an integer, it is also rational, okay? Now, from there, we needed to do other things. And I'm gonna read from the book so I get it right. This is called The Joy of X, and this is actually a really interesting mathematical, nerdy kind of book. Goes through the different types of maths and what they're used for. So I'm gonna just kind of read the little part about where roots come from. It says, one of the earliest such problems perplexed the citizens of Delos around 430 BC. Desperate to stave off a plague, they consulted the Oracle of Delphi, who advised them to double the volume of their cube-shaped altar to Apollo. Unfortunately, it turns out that doubling a cube's volume requires them to construct the cube root of 2, which was not possible for them to do. So you know what they did? They invented our irrational numbers. Now, notice a couple of things. Rational is a cube. Irrational is literally the word rational with ear put before it. That prefix means not, so not rational. That symbol there, which we say is Q prime, it means the opposite of Q, the opposite of rational numbers. So, our definition cannot be written as a quotient of 2 integers. In other words, not a fraction, okay? So this is going to include all of our decimals that do not repeat, do not terminate. It includes pi. It includes roots that are not perfect, okay? So some examples, and I only put a couple because we're not gonna get too far into our irrational right now. Pi is, of course, our favorite one, favorite irrational number. Square root of 3, cubed root of 2. Square root of 16 wouldn't be here because square root of 16 equals 4. So it would be here, it would be rational, okay? And then 0.1234870 ... it doesn't repeat, it doesn't terminate. That one would be irrational. Now, if you're thinking I'm gonna stick this box of rational inside this box of irrational, I'm not. These two are not subsets of one another. They are what's called mutually exclusive. If you're rational, you can't be irrational. If you're irrational, you can't be rational. So these two together is what makes up our real number system. So they kind of go next to each other. So the real numbers is that capital R with the double strike through. I'll hold it closer so you can see it. And it includes rational and irrational numbers. It really includes everything that you have learned about so far. 30 seconds. The thing that doesn't include is just our imaginary numbers, which we're going to learn about this year. And that is it for our system, our development of our system of real numbers.